Hello, so this is joint work with my colleagues from Cornell Tech and Royal Holloway, Paul Grubbs, Brice Minot, and Kenny Patterson. So businesses and organizations have many reasons to store their data, which often is our personal data, in the cloud. So a client might outsource its data and then retrieve records whose values fall in a particular range. Range queries are one of the fundamental query types. After point or equality queries, some think they're the second most common. Now, it doesn't matter exactly how things are stored in the cloud, what kind of database it is. It could be a key value store, it could be a traditional relational database. As long as records are retrieved by range, the details are less important. So for example, suppose that the client is a hospital and is outsourcing patient records to the cloud. Now maybe hospital administrators want to retrieve items based on, say, the age of the patients. So if the age was within the range 0 to 4, they'll ask the cloud for their patient records, and the cloud will oblige and return records for those patients. Now, medical data is, of course, sensitive, so the hospital will plan to use some kind of encrypted scheme for outsourced data. So maybe the range queries will be encrypted, they won't be visible to an observer, maybe all the data at the database is encrypted, and maybe the responses will be encrypted too. But even if the encrypted search scheme being used is one of these fancy techniques that hides a lot, like if you're using fully homomorphic encryption or if you're using ORAM to hide access pattern, something that still leaks in a lot of these schemes is the volume of a range query. And the volume is just the number of items that's returned in response to the range query. And this is what our attack will exploit. It could be leaked to just a passive network adversary monitoring traffic who sees how many records are returned. It could be leaked to an honest but curious server, the one that's actually storing the data in the cloud. Or it could be a snapshot attacker who sees diagnostic tables that keep records of the volumes of past queries. Volumes can leak in a number of ways. Now, our attack is going to use this volume leakage to reconstruct counts of items in the database. This problem has been examined before, and our solution improves on the previous best attack in a number of ways. We validated our attack in both theory and practice. So we carried out an experimental evaluation on real medical records, and we also have a strong analytical model that gives a theoretical backing to explain what we observed in those evaluations. Lastly, we have two additional attacks, which I'll mention at the end. So first, up front, here's the full list of assumptions we use. First, the database is static. So no records are added or removed or updated. We assume the data isn't changing while these range queries are happening. But I'll come back to this at the end with one of the additional attacks that takes a step from static databases towards dynamic databases. Our second assumption is that every range query occurs with non-zero probability. So every range query needs to occur at least once. And our third assumption is that in the database, there's at least one record with each of the values from 1 to n. So throughout the presentation, n will be the number of possible values in the database. So in the age example, it would be, say, 0 to 100, and n would be 101. We'll assume that the values are just the integers from 1 to n. Now, this assumption is just for this presentation. If you want the details for what to do and how our algorithm handles the case where not every value appears in at least one record, I'll refer you to our paper. So as I mentioned, the problem of database reconstruction with volume leakage isn't new, and the previous state of the art was by Kolaris, Kolios, Nissim, and O'Neill, presented here at CCS 2 years ago. I'll call this KKNO. So the KKNO volume attack requires range queries to be uniform. And this is because it works by not just looking at the actual volumes, but by precisely estimating the frequencies of these volumes and then reconstructing counts based on that. If the query distribution is slightly off from uniform, then the attack completely fails. Now, for this reason, because they need such precise estimates of the frequencies of the volumes, they need to see a lot of queries. So this is n to the fourth log n queries. And this attack is also computationally expensive. It depends on the total number of records in the database, which I'll refer to as R throughout. On the other hand, our attack needs only to see the volumes. We don't do any estimation of the frequencies. It works for practically any query distribution. Recall assumption 2 that every range must appear with non-zero probability. So this means that we need much fewer queries. For the sake of putting a number on how many queries we need, we have to assume something about the distribution. So to compare to KKNO, if the queries are uniform, then we need only n squared log n. Now, the query distribution, the queries don't actually have to be identically distributed or even independently chosen or anything. We just need to see all of the volumes. So we need for every range to be queried at least once. And lastly, our attack scales well. It actually performs better when there are more records in the database. So we have a database reconstruction algorithm that takes as input the set of all range volumes. We're assuming that we've seen all the queries at least once, and outputs the element counts up to global reflection. Now, this up to global reflection means that there will be one bit of information missing, because with just volume leakage, it's impossible to distinguish the low values from the high values, so from 1 to n. Now, before describing how our algorithm actually works, let's quickly look at how many queries will be necessary to see all volumes for some different distributions. So for uniform distributions, by a simple application of the coupon collector bound, we need n squared log n queries so that each one has been issued at least once, and we know we have a complete full set of all possible volumes. With a power law distribution, like a standard Zipfian distribution, where the ranges are ordered in some way and the probability of the kth range is proportional to 1 over k, then we need only a multiplicative logarithmic factor, more queries, to see all of them. Now, this is significant because such power law distributions are thought to be a lot more common and arise more naturally in practice. So now back to our algorithm. The idea is to identify certain special volumes, what we call elementary volumes, from among the set of all volumes. So an elementary volume is just the volume of an elementary range, which is what we call a range of the form 1 to I. If we recover elementary volumes, then we can recover element counts in the database. Given the volume of the range 1 to I and the volume of the range 1 to I minus 1, we just subtract them and we get the number of elements with value I, and vice versa. Now, to find these elementary volumes, we'll use 3 properties. The first is that they're complemented. This follows from the definition. The range 1 to I has a kind of R complement, as we call it, which is the volume of the range 1 plus I to n. The sums of the volumes of these two ranges add up to R, which, recall, is the total number of records. The second property is that each range either is an elementary range or is the difference of 2 elementary ranges, and the converse also holds. So we're going to build a graph to try to identify these elementary volumes. So we start with building the nodes, which are just all observed volumes. Now we'll use the 3 properties along the way to help us. So first we add edges between 2 nodes if their absolute difference was also an observed volume. Then by property 2, we know that the elementary volumes will form a clique in this graph. And by property 2, we know that it has to generate all volumes. Now, I mentioned CLIQUE-FINDING, and some of you may be stepping back and scared because the clique decision problem is NP-complete and it's self-reducible and you don't want to do anything exponential time. After all, we want these attacks to be practical. So don't worry, we resorted to somewhat generic CLIQUE-FINDING only as a last resort, and it was very rarely necessary. So keep that in mind. So our algorithm takes as input the set of all range volumes, and it's going to output elementary volumes from which we can get element counts up to global reflection. Now, the 2 main steps of the algorithm are pre-processing and then, only when necessary, some kind of clever CLIQUE-FINDING. So pre-processing works by maintaining two sets of volumes. We have the set of necessary elementary volumes, volumes we know must be elementary volumes, and candidate elementary volumes. So we'll reduce the set of candidates and build up the set of necessary volumes in a precise way. That's the details are in the paper, but I'll do an example so you get a flavor of how we do these two things. We'll go back and forth between augmenting the set of necessary volumes and reducing the set of candidate volumes. So let's do an example. Suppose this is our set of observed volumes. All of them are there. The candidate set will be blue. So first, remember the first property of elementary volumes. If a volume does not have an R complement, then it cannot be an elementary volume. So any volumes for which there doesn't exist another volume that equals R minus the first volume, we can throw out of the candidate set. Now let's seed the necessary volume set with the smallest complemented volume, which, up to reflection, must be the volume of the range 1, 1. If you think about it a little bit, you'll understand why. And the largest complemented volume, which must be the total number of records, because it's also the volume of the range 1 to n. Now we can remove all nodes not adjacent to all necessary volumes. And at this point, maybe you can see the click, but I'm just going to talk through the algorithm till the end. Another way to augment the set of necessary volumes is to look for volumes that arise only in one way in the graph. So for instance, the volume 5 arises only as the difference of volumes 12 and 17. Since we saw volume 5, we must add 12 and 17 to the set of elementary volumes, of necessary elementary volumes. And now we're done. We can check that all observed volumes were generated by this clique we found. And from those elementary volumes, we get counts of elements in the database up to global reflection. So to evaluate our algorithm, we ran it on real patient records from the United States Healthcare Cost and Utilization Project's nationwide inpatient sample. This is also used, for instance, by KKNO and in a lot of attacks on encrypted search schemes and encrypted database attacks. So we picked 10 attributes on which range queries are meaningful, and we evaluated pre-processing on at least 2,500 datasets for each. So here, one dataset is the records of one hospital over 1 year. The attributes ranged from n equals 4 values to n equals 365 values. Now, for the sake of this presentation, I'm going to completely ignore sparse datasets, which are the ones that don't meet assumption 3, where there isn't at least one record in the dataset that has each value from 1 to n. So I'm going to completely ignore those. We deal with them in the paper. So the results of pre-processing, either we were able to find sets of necessary volumes and candidate volumes that coincided, so we know we're done, we found the elementary volumes, we can rebuild the counts, or we didn't. So for sparse data sets, you need to look at just the bars with the close together lines, the dense lines. That's what we're focusing on here. So the dark green with lines diagonal and up to the right. So for these dense data sets where assumption 3 holds, pre-processing found the set of elementary volumes in over 98% of data sets. We didn't need any sort of clique finding for this beyond our really efficient pre-processing algorithm. So for the 1.5% of dense data sets where pre-processing didn't find the set of elementary volumes, we had to do some kind of clique finding to keep going and look for these elementary volumes. So on graphs with few nodes, say less than 20 is what we did, then we exhaustively find all cliques and look for the ones that generate all the observed volumes. If they have more, then we used an efficient sampling method to sample maximal cliques and hope that we stumble on the one that contains the clique consisting of the elementary volumes. So here are the overall results. Again, if you look at just the bars with the dense lines diagonal up and to the right, that's dense data. The rest is sparse data, which again is explained in the paper. So there are 3 colors here, red, blue, and green. Well, light green and dark green. But green means we found the unique elementary volumes up to global reflection. Blue means that there were multiple solutions. Now, this can arise because the set of volumes generated by database counts can come from multiple databases. So 2 different databases, and here I mean different, not just reflected. 2 different databases can have the exact same set of generated volumes. So in some cases, there were multiple solutions, and the blue bars mean we found all of them. Now, red means that our algorithm didn't find the solution. Now, of course, there is still a solution. This clique has to exist. But we wanted to keep things practical, which means we wanted it to run in less than an hour on a 5-year-old laptop. So if we threw more processing power at this, all the red would turn into either green or blue. Now, the analytical model we developed to provide some backing to the results of what we saw assumes that the database contains uniformly distributed values. Now, this is to maximize the number of volume collisions, which is kind of bad for our algorithm. So we model the volumes as independent Poisson variables, and then we can come up for estimates of properties like the number of volume collisions, the number of R-complemented volumes, which will be the initial number of nodes in the candidate volumes, the number of nodes in our graph, and the number of edges in the graph. Now, what falls out of all these assumptions and approximations, the culmination is that there are likely to be no other cliques in the graph other than the one formed by the elementary volumes when R, the number of records in the database, is at least n squared. So this is why I said that our attack performs better when there are more records in the database. And this is reflected in our experiments, but it applied more to sparse data than dense data, so I won't say much about it here. So in addition to this main database reconstruction attack, we also have 2 additional attacks, or bonus attacks, update recovery and CDF matching. So the purpose of update recovery is to take that step from static to dynamic databases. So suppose you ran our main algorithm, you have the database counts, and now suppose that you see a new record is inserted into the database. What this attack does is identify the value of that newly inserted record with fewer queries than are necessary to run the entire attack. So if we assume that range queries are uniformly distributed, because we have to assume something to say how many queries we'll need, then this will be O of n queries. Now, the second attack has a different goal. This is the CDF matching attack. And the goal for this is not database reconstruction, but it's online query identification. So you see a query, and based on some additional data, in this case, we assume you have an auxiliary distribution, so you have some idea what the counts of elements are in the database. So maybe this is from public statistics or from an earlier leak of the database. You have some idea of the distribution. Using that, you can output a set of possible ranges corresponding to the one you just saw with a particular volume. And we can bound the error of this CDF matching attack and the number of ranges it outputs using a standard statistical inequality. So in summary, ranges are a fundamental query type. After equality queries and point queries, they're one of the most important classes of queries. Most schemes leak volumes of queries, even if you use strong techniques like FHE and ORAM. Volume is hard or usually expensive to hide. Our main attack reconstructs element counts from volume leakage. Compared to prior work, our attack is more robust to different query distributions. We need just the assumption that every range query will be seen at least once, so we have a complete set of volumes. It requires leakage from fewer queries. In the case of the uniform query distribution, this is n squared log n. And our attack also scales better. It performs better when there are more items in the database. So our work shows that volume leakage attacks, which maybe were previously dismissed because of poor performance or unrealistic assumptions, should be considered a real concern. Thank you.
We have a question.
Hi. So you talk about scaling better with large R, but I don't know, that seems a little unfair because your algorithm actually large R is the easy case for your algorithm, and the hard case is when it's right around n squared and there's a lot of overlap in the volumes, right? There are multiple ways for ranges to produce a certain volume,
Okay.
right? That's when your algorithm gets hard and it's hard to eliminate nodes, and that's when you'll probably have to do your general CLIQUE-FINDING
To find all solutions.
stuff, right?
Yeah.
So what can you say about not really the large R case, but the worst case?
Well,
Like,
I guess the worst case would be there are multiple solutions. There's not one set of unique elementary volumes. We didn't generate any databases to explore this worst case. We just used what the hospital's distributions were. So I don't have much to say about it. Actually, we didn't do a deep dive into the worst case.
right.
Yeah.
So I think it's an interesting just combinatorics question.
Yeah.
About how bad can it get?
Yes.
Like, can you make a distribution that has the worst possible set of repeated differences?
Yeah.
Yeah.
Yeah. So there are some lower bounds for this. The KKNO work they showed for not just dense data, but for sparse data. In the worst case, you need enter the 4 log n queries to be able to distinguish that. And the kind of pathological distribution they built for that lower bound was either every item in your database has value n over 2 or n over 2 plus 1, roughly, something like that. 2 adjacent in the middle. And then you need the full enter the 4 log n queries to distinguish them. But there are also some cases where there's fails, where you can't factor this polynomial you needed to factor, which might correspond to multiple solutions. There might also be other types of worst case distributions.
Thanks.
Yeah, thank you.
Thank you. There's another question over there.
So this is beautiful work. Thank you very much for it. I have a question a little bit about the defense on and trying to keep this information private. Is there any hope, or is the only solution to limit the number of queries that are permitted, or is there some other approach that you'd recommend?
There are a few approaches for countermeasures for preventing the attacks. So you can batch queries together, you can set limits, you can modify ranges. Now some of these are kind of solutions you can drop in place, and some of them require a bit more work. As far as I know, there's no elegant solution, but that just may be
doesn't work for colluding adversaries either, right?
I have no idea.
Yeah. Okay.
Good question.
Okay. Thanks.
Yeah. Thank you.
I know you used real patient data. Did you also have the encrypted queries from the hospitals, or were you kind of generating your own queries to test this against?
Good question. So it's really hard to find data sets of queries because often this reveals a lot of sensitive information about what's being queried. So we didn't have any queries. We just randomly generated them. Thanks. Yeah, thank you.
All right. Any last question? No. Thank you again.